We are counting down the 7 most mysterious and scientifically puzzling features of 3I Atlas, the interstellar traveler that continues to baffle even NASA's finest minds. This is not just another comet story. It is a collection of real data points that stretch the limits of known physics and leave astronomers staring at their models, asking questions no one expected so soon after. Oumuamua and Borisov, from strange alignments in the sky to chemistry that rewrites comet theory. Each entry in this countdown pushes us closer to the edge of cosmic understanding. Let us begin with the first enigma, the one that links a 1970s radio mystery to a modern-day interstellar visitor. Number 7. The WOW signal coincidence. When 3I Atlas was first tracked, entering the solar system, scientists noticed something both exciting and unsettling. Its inbound trajectory passes within roughly 9 degrees of the coordinates where the legendary WOW signal was detected in 97. That burst, recorded by Ohio State's Big Ear telescope, lasted just 72 seconds and has never been repeated. The overlap immediately caught public attention. 2 unrelated cosmic events, separated by nearly half a century, happening in the same small region of Sagittarius, or could they be linked? Statistically, the sky is vast, more than 40,000 square degrees, so a 9-degree separation is far from proof of connection. Astronomers call this kind of pattern posterior selection bias and the human tendency to notice coincidences only after something becomes famous. In reality, it is almost certainly a cosmic coincidence, yet it's one that has fueled thousands of online theories, podcasts, and late-night debates. For scientists, it's a reminder of how meaning and mystery can sometimes overlap, even when data says otherwise. The WOW link may not prove anything, but it ensures that 3I Atlas enters the story of Interstellar exploration with a myth attached to its name. Number 6. The flat orbit mystery. If the WOW coincidence grabbed attention, the comet's orbital path turned heads for a completely different reason. Unlike most interstellar objects that swoop into the solar system from steep, high-inclination angles, 3I Atlas glides in almost perfectly flat, just over 3 degrees above the ecliptic plane, the same thin disk where the planets travel. For context, Oumuamua crossed at a staggering 122 degrees, while Borisov entered at about 44 degrees. 3I Atlas, by comparison, follows a razor-thin trajectory nearly parallel to Earth's own orbit. The odds of a random interstellar body arriving this close to the ecliptic by pure chance are less than 1 in 200. Some astronomers explain it as observational bias. Earth-based telescopes naturally detect more objects near our orbital plane, yet even after accounting for that bias, this orbit remains statistically unusual. It's almost as if the comet were purposefully aligned with the solar system's natural. Scientists are cautious, though. There is no evidence of intent, only geometry. Still, this precise alignment makes 3I Atlas stand out among every known interstellar traveler, raising an important question. Did it just happen by chance? Or are we seeing a hint of a larger pattern in how these objects find their way through stellar space? That question sets up the next, even stranger puzzle. What happens when light meets the dust of 3I Atlas number 5? The polarization puzzle. One of the earliest surprises about Atlas came from its light polarization. When sunlight reflects off dust particles, it becomes polarized, meaning the light waves align in a particular direction. For typical comets, scientists can predict this polarization curve with great accuracy, but when Atlas was measured, its polarization did not match any known model. At first, its light behaved like a dusty, carbon-rich comet, then abruptly switched to a pattern more typical of metallic grains. This transition happened in only a few days, which is physically difficult to explain. One theory suggests that the comet has alternating layers of dust and metal, perhaps a relic of a destroyed planet from another system. Another idea is that the outer surface of Atlas was coated in organic frost that evaporated, revealing a denser mineral core beneath. But no telescope on Earth or in space has yet captured such a sharp polarization shift. It remains one of the most unexplained signatures of the object. Number 4, the chemical code. When spectrographs at the Very Large Telescope in Mauna Kea Observatory analyzed the light coming from the comet's coma, they detected ratios of carbon monoxide to carbon dioxide unlike anything recorded before. For normal solar system comets, these ratios hover around 1 to 1, But in Atlas, the value spiked beyond 20, meaning it was outgassing. Pure carbon monoxide at a level no model can account for. This implies formation in a region of extreme cold, perhaps on the far edge of another star system where sunlight barely reached. The discovery challenges long-held ideas about interstellar bodies, suggesting that not all comets share the same chemical DNA. Instead, some might carry frozen records of environments, completely alien to our solar chemistry. Number 3. The brightness enigma. As Atlas neared perihelion, it defied every predictive curve. Rather than fading as dust evaporated, it grew brighter, peaking weeks later than models expected. For comet scientists, this is backwards. Most comets flare up before they reach the sun, then fade. But Atlas seemed to grow stronger with heat, as if some buried fuel source was awakening. This late brightening sparked theories ranging from crystallized carbon monoxide suddenly venting, to volatile pockets beneath the surface igniting under pressure. Yet even those explanations fail to fit the light curve perfectly. One possibility is that Atlas rotates unusually slowly, exposing new regions to sunlight. Whatever the cause, this brightness pattern is unlike any interstellar visitor we have ever seen before, and it deepens the mystery that has already shaken traditional comet. Physics number 2. The giant among travelers. The closer astronomers studied 3I Atlas, the more its sheer size began to challenge every statistical expectation. Early brightness modeling, taken from dozens of observatories, indicated that its nucleus could be nearly 5 kilometers across, more than triple the size of any interstellar object ever observed. In terms of mass, that is roughly 30 billion tons of material, an interstellar heavyweight unlike anything we have detected entering the solar system. For comparison, Oumuamua and Borisov both measured under 1 kilometer in diameter. According to existing population models, smaller fragments should vastly outnumber giants like this. In fact, the odds of spotting a 5-kilometer interstellar body before finding thousands of smaller shards are almost zero, and yet 3I Atlas is here. Some researchers suspect an observational bias. Perhaps large objects reflect more sunlight and are simply easier to detect. Others argue that the unusually flat orbit may have increased its visibility, but the real surprise is how consistent the numbers are, even when accounting for reflectivity, coma brightness, and dust scattering. The calculations stay firm. This object is massive, stable, and incredibly rare. That immense weight also explains one of its most mysterious behaviors, why it hardly moves off course. No matter how violently it vents material, that stability sets the stage for our number 1 anomaly. Number 1. The unshakable path. On October 3, 2025, Atlas made a near approach to Mars, passing within just 28 million kilometers, an extraordinarily tight flyby for a body that came from another star system. Later projections suggest future approaches to Venus and even a distant swing near Jupiter. Statistically, the odds of an interstellar comet naturally threading through such a precise sequence of planetary flybys are microscopic, less than 5 in 100,000. But the greater mystery lies not in the geometry, but in the steadiness of its path. As Atlas approached the sun, scientists expected its outgassing jets to act like miniature thrusters, nudging the comet off its predicted course. For normal comets, this non-gravitational acceleration can shift their position by dozens or even hundreds of kilometers per day. Oumuamua showed this clearly, with wild trajectory changes during its short visit at Atlas, however barely flinched. Across months of tracking by more than 200 observatories, its deviation remained almost immeasurable, less than a fraction of a percent compared to what models predicted. The explanation again circles back to mass. With tens of billions of tons behind it, the comet behaves like a cosmic freight train, gliding through the inner solar system, unfazed by the push and pull of its own escaping gases. To some, this sequence, the flat orbit, the perfect flybys, and the unwavering course, looks almost too precise to be random. But astronomers emphasize that there is no evidence of design or intent. Only physics and probability stretch to their limits. Still, Atlas forces an uncomfortable truth into focus. The universe is far more unpredictable than our equations like to admit from the chance. Alignment with the wow signal to its chemically unique dust. From the impossible polarization patterns to the silent stability of a nucleus, larger than a mountain, 3i Atlas defies nearly every rule of comet science, reminds us that discovery does not always come from what we expect. Sometimes it arrives from the cold void between stars, carrying mysteries no model can fully explain as telescopes continue to follow its path beyond the sun. One question remains. If this is just the third interstellar visitor we have seen, what on Earth or beyond it might come next?